Okay, so we're very honored to have Professor Gordana Todorov, who will give a distinguished lecture series in algebras and categories. And she's a distinguished professor at Northeastern who has made many fundamental contributions to the area of constant algebras and representation theory of algebras. And we're very honored to have her here.
Thank you. So this sounds like it will be interesting to give a series of lectures. Are the lectures supposed to be 50 minutes or 1 hour? 1 hour. Okay. Okay, so I will start. Now, of course, first I just want to hit one. It's quivers. So the quivers will be, with Q0, Q1, with Q0 vertices, Q1 arrows. Now for this talk, I will be okay. At the beginning, I will be talking about simple ways. So at the beginning, I will talk about simple ways, which means that there are no, i.e., there are no things like that you can see usually in the list of B and C, or this is sometimes written as 1, 2, or 2, 1, or 1, 3, or something like that. So at the beginning of this lecture today, I will talk about that, but then at some point I will switch to these are called valued quivers, and then I'll switch to that. So for this, I'm just taking singulars here. And I'm assuming that Q is acyclic and pi. So acyclic means that there is nothing like that, and there is nothing like that. Nothing like that. But this is okay. So acyclic means acyclic in the orientation sense. So this is okay, and then the typical is always something like that, etc. Or you can have several arrows coming to the same, something like that. So I now I want to recall that definition.
Is the last one simple ways?
Huh?
The last one?
Yes, yeah, this is simply because they're not, it's not oriented. Oh yeah, this is considered simple ways. It's not that.
Mhm.
This just means 2 separate arrows. Okay. So this is still considered simple ways, but it's not that one. Actually, that's why I get confused with this one, because this is like that. Yeah, so you can have that. This is like this is chronicle, which is still considered to be simple ways. Okay. So now I want to talk about representations. So for that, for the beginning, I'm going to take K to be a field which is algebraically closed. So I'm going to talk about algebraically closed as long as I'm talking about singulars. And then once I go to the valued figures, then we will have R and C and non-algebraically closed. So for now, I have algebraically closed, and then the representation means a collection of VI I in Q0, so for each vertex is VI, and then Bj to Vi, and I'm going to write here V alpha. So this is a collection of maps for each arrow from J to I in Q1. So these are the K vector spaces. And these are K linear maps. So, I also want to talk about the morphisms between representations. So if I have representation B and representation W, I want to talk about morphism between these two representations, which means that for Vj to Wj, there's Fj. Now, V alpha goes to Vi, and this should go to Wi, and this is Fi, and here the definition of this W is W alpha. So that means that for every alpha, which is J to I inside of Q1, we want to have commuting diagram like this, where each of the Fi's are linear K. And then that is morphism between representations. And that Q stands for the category of finite dimensional representations of Q. Okay, so finite dimensional means each of these VIs is finite dimensional. I will not be talking about infinite dimensional representations, but usually people put capital R for infinite dimensional, but as long as I keep my little r, then it is finite dimensional representations. And this is nice abelian. So now I want to kind of give example of the morphisms, sorry, morphisms which are not actually morphisms. So I'm just, for this beginning, I'm going to do my favorite 1, 2, 3. And so I will use to describe representations. So, yeah, I mean, you saw many of these things yesterday, but I think because I want to combine things, if it's okay that I will be leaving things out. Okay. I guess I'm using now K. Then K. Okay, so this is S1, S2, and S3. And then K here and K here, and identity or any non-zero element here is P2. And then K and K identity is I2, and finally K is P3. So these are the indecomposable representations, and this figure is K. So now I just want to give some examples of homomorphisms. So if I take S1 and map it to P2, So that means my S1 looks like that. P2 is like that. So I need my F1, F2, and F3. Because this is 0. So if I put here for F1, I can take any F1, any non-zero F1. Okay. And I can take here 0. And that's okay, because this is 0, so this commute. So this means that this map is a non-zero. So that says that the half, and of course this is 0 here. So that says that the half of P1, I should also point out that S1 is also projective, so it's P1. Okay. So half of P1 in the representations of Q to P2. I can put here any K, right? So this is isomorphic to K. So that means there is this, there are non-zero maps here. Now, this is a question that I get often when I talk about it, and then people ask me, well, what about going from P2 to S1? So if I take P2, okay, and this is identity, and S1, okay, here, and this is 0. Then, okay, of course, this is 0, 0. And here I can only have 0. And then if I put F1 here, I need this to commute. So I have the identity composed with F1 has to be equal to 0 or 0, which is 0. Therefore, F1 must be 0. So I'm looking at the same two representations, S1 and P2, and using just the definition map between representations, and using this, you see, this here, what I wrote here, this is the important step for the map between representation. This is equivalent when you're talking about modules over a ring, it's equivalent to saying that it is homomorphism of a module, so that f of alpha, f of 3 times x is equal to 3 times f of x. So so this commuting diagram is what takes care of that. Okay, and so this really shows that there is no representation map from P2 to S1. There would be if I talk only about K, only like K behavior map, not representation.
There's one map, the 0 map.
Here, there's
No other one.
Zero map. Yeah, I keep forgetting to actually. There is one, I wrote it. And then, but then I also want to do this one, P2 to S2, right? And if you take P2, which is now KK, and you take S2, which is K, of course, these are zeros, then, okay, this is an identity here, I can put F, which is non-zero, I can put F2. Now, this is 0, so this is 0 map, this is 0 map, so here I have identity composed with 0 is equal to F2 composed with 0, and that's okay for any F2, which is non-zero, for any F2. So that means that from of P2 to S2, Q is also isomorphic. So this is kind of just a simple case, and so usually what you can see, notice, if you have, okay, so this is slightly informal, okay, what I'm going to say. But if you have like something like that. That you can map this to the things which are at top. You can map to this or to this or to this. So you know, and you can generalize this to kind of larger bigger, right? But essentially, if you can map to the top of your quiver, I'm always drawing my quivers going downward, so when I say top, I really mean top of the quiver. But the maps that you can have it in are only this K can be mapped here, or K and K can be mapped here. So some, what I will probably mention often, that quotients of this representation are these top parts of the representation, and some representations are these bottom part of the representation. Okay, this K here is the simple submodule of this, it's the circle of that. This K here is the top of this module. Okay, so maybe now I will put them here, because last time I put, let's not put the older things that I was going to say, but yeah, I just want to put again that the air I did last time, just so that you see that this. Okay, so you can see here that with this K here is a sum representation of this one, right? So it kind of matches this what I was saying here. This is some representation here. I'll even put this on. This here is this S2 that I showed it P2. Of course, when I don't put anything between case, I do mean a non-zero. You can go from here to here, and you can see that this is nice surjective map. This maps onto this. Similarly, this maps onto this. This maps onto this. And this is a submodule here because this K here is at the bottom of this representation. And this is kind of maybe slightly informal way of saying, but I just kind of want, because this, after you do more of these, this look too close. Okay. These are short exact sequences. So this was just illustration of what I did here. Okay. Have any questions about this? No. Okay, so now the next thing that I wanted, oh yeah, I wanted to put one example. Of course, these are indecomposable. Sometimes we get into the habit of writing only indecomposables, but you know, you can have anything. I can have K squared, K2. K4, and so the only thing is you have to have appropriate size matrices, and that is the representation. Now, I want to do one like this. K squared. I just want to say this is inside of that. I can put any matrices here. Because I'm not talking, this is not indecomposable because these are not indecomposable, so this is not indecomposable. So it's just the representation which is sum of several. Okay, but now I want to do one which I actually want to describe. Okay, so here I'm going to take this K, so it goes here, and it goes into the first coordinate, and 0 here, and then here. I'm going to go with the first coordinate to 0, a second coordinate to x. So now when you look at this, maybe it's not so obvious, but this will be actually sum of these two. So I just want to kind of say what is formal way of writing the right side. So, okay, so let me just say this is isomorphic. So, plus now the dimensions always work fine, but I just want to point out that if we have a representation V, with V1, V2, V3, and we have W1, W1, W2, W3, and we want to look at B, like some W. It's the natural thing, it's the most natural thing, I just want to write it. On each coordinate, it will be the direct sum of these. Slightly longer. Then here I have V plus W2, and here I have V3 plus W3. So it's exactly what you expect, right? And then the only thing is what are the maps? The maps are again the most natural. Diagonally you put here, okay, if this is alpha and this is beta, then you put here V beta and W beta is zeros here, and on this one, okay, V alpha and W alpha. I'm sorry, it's a little too small, but you just put it there. Okay. Now, of course, you know, you sometimes they're not written diagonally, but then you do isomorphism. Yeah, so two representations will be isomorphic. If they're isomorphisms with one for the other, then everything copies. So I just wanted to point out, so like here you can see that this one is actually isomorphic. Even though first it wasn't big look back. Okay, so that's about the representations, and then there is the theorem. So here is the Gabriel's. Which says, well, the simply ways. Maybe it's not stated simply ways, but because I will be talking about the others, so I want to say simply ways. And finally, then U is representation finally. I only finitely many isomorphism classes of in decomposable modules, in decomposable representations. Many isomorphism classes of in decomposables. If and only if U is a big remarks. Or I can say graph with any orientation, so it really does not depend on orientation. A, D, B. And so that's the first part. Okay, so that's like part and part is there is a rejection will be composed of representations of U and rules of the rule system. System of U. Something I was going to talk today at 3 o'clock, and I was going to say, well, just as even. Okay, so tomorrow there'll be more stories about rules, but I just want to point out here that you see S1. Now the correspondences, you take a representation and you set it to the dimension vector of the representation. Okay. So if I take S1, so I'm going back to the example that I did here. So S1, well, the dimension of S1 is 1, 0, 0. And that will correspond to the simple root alpha 1. Now, S2 corresponds to 0, 1 to 0. That's the dimension vector of S2. And that will correspond to alpha 2. S3 the 0 and 1 will be alpha 3. Now, P2, the dimension vector is 1, 1, 0. So that will correspond to alpha 1 plus alpha 2. And then tomorrow we'll hear that that is also positive to alpha 1 and 2 are roots, but because there is an edge on the quiver between 1 and 2, actually for the root you don't need orientation, so it will be just graph. So because there is an edge on this graph, that's why this will be also root. And then R2 is 0, 1, 1. And that will be alpha 2 plus alpha 3. And P3 will correspond to 1, 1, 1. And then it will be alpha 1 plus alpha 2 plus alpha 3. To write this, I am using, so here I really want to emphasize, I'm using simple roots as basis. So I'm not using R, it's not like in R3 that I'm using x-axis, y-axis, and z-axis. I'm using simple roots of this one corresponds to this. These 3 elements I use as a basis. And that is how I get that P2 is some of these 2, but that means this basis, not in the study. You look at the pictures of roots, sometimes you see alpha 1 is like that, alpha 2 is like that, so it's not the standard R. Okay. Okay, so that's okay. Okay, so now yes, I did that. Okay, and then the remark, I can just write my remark. There are important das reverse which are not simply non-simple ways. So that's one thing, and also which something that we will hear tomorrow that I expected to hear today, important road systems. Road systems. Which are not ADE, so it's B, C, F, G, and maybe those will be even more. Right? So the point is that, and also these important road systems are related to important the algebras. So there is always extra important things which are not covered by simple ways curves. So because of that, I decided to talk. So instead of talking just representations like that, I want to talk now also about representations of valued figures. You see, I start with the beginning here, so then after that I form. Okay, so if I my value to figures, so I didn't put my numbers here, but I think this was supposed to be 1.6. So whatever numbers came there. Okay, so I will talk about the value figures. Yes. And quivers. So again, I will be using time. So evaluation. Okay, a graph. A value. Graph. So I'm not putting the orientation there. I will denote it by gamma, gamma 0 and gamma 1. Consists of gamma 0 are vertices and gamma 1 are edges. And then the word value, so this is just a graph. This part here is just, yeah. But now the value part comes in. And so I need a collection of i's for each I in gamma 0. And then for each ordered pair I j, there is ordered pair. Okay, I think now I can really take this. It is ordered pair of B I J B J I, where all F, okay, so that is for each ordered pair, I have these. So that means for every I J in gamma 1. So that means for each edge, there is a pair of positive. So let me just write Fi, Bij, and Bji are positive integers. Okay. So for each vertex, there is a positive integer. And on each edge, there is a pair of positive integers. Okay. Such that Bij times Fj is equal to Dji times Fi. So what will happen very soon, I'll write that. So these Fi, Fj's will be the dimensions of the field that I put on each on each vertex. So instead of having the same field, it will be like R and C and so on. And these will be the dimensions of the bimodule that I'll have in between. So instead of just having a line, there will be my bimodule. I'll do this formally. Okay, so I just want to point out that. So, okay, so an example. So I'm taking now it is 1, 2, 3. But this time it will not be a 3 because I'm going to put some numbers here with like this. So I'm going to put F1 to be 1, F2 to be 1. See if I want to do that one first or the other one first. I mean, I'll do actually one will be D3, one will be C3. So, yeah, but let me just see which one I decided to do first. Yeah, that's what I decided to do that. Second. And F10. So now, if I have these numbers on a graph, then I can put any orientation and I get valued quicker. Okay. So, yeah, I didn't have to put immediately. Yeah, I did like this. Okay, let me. Yeah, this is just the graph. So this is my graph, which is the sphere. Okay, now I need here a pair of numbers such that this times that is the same as this times that. So if I put 2 here and 1 here, 1 back to 2, this, and I can put here 1. Okay. So now this is for the pair 2, 3. I have D1, 3 is 1, and D3, 1 is 2. My F3 is this, and this. And I'm also right. So I have that D2, 3 is 1, and D3, 2 is 2. And here F of D1, 2 is 1, and is D2, 1.
Is the identity okay now? Can we check the identity D2 3 times F3 is equal to D3 2 times F2? Or the F, can we check the identity D2 3 times F3? Can we check the identity? The identity,
This
yeah.
is the same as the.
Yes, good, yes, perfect, yes, great. Yes, sorry, yes. I got confused.
Yes, it's 2 times F2, right?
Perfect,
So
yeah.
this is 1 times 2 is equal to
Mhm. Yes, sorry,
Okay.
I got confused, sorry.
You're just checking.
Reversible, the diagonal matrix from the left.
Yeah.
Okay. Okay, so this is how you do valuation. Okay. And maybe I'll write it here immediately. The other one. So we also 1, 2, 3. And if I put here 2, 1, and still keep here 1, 1, then I need this F3 is 1, and F2 is 2, right? Because I need this turns that to be the same. And F1 will also have to be 2 because of this 1, 1. Okay? So these are two different valuations, right? This will be C3 and this will be D. So now, I guess you would have. So, when you look at Lee algebra books, then this is larger. I think this one will be like that. And this one will be like that. Okay. So the only thing is when I put them like that, I always get worried about this chronic. So I prefer to write the valuations. Okay, and this will correspond. So whenever you have these different numbers that appear here, then what will happen is that there will be these valuations which are different. We will have different fields, and you will have long and short roots. Right? Okay, so now, since I want to talk about representations, one has to do. I see you're looking at the clock. Is that 15 minutes?
Yes, yeah, more than that, more. We started late.
You started late. Okay.
Yeah.
Let me try to. Okay. So in order to talk about representations, I need also to talk about valuations. So this was my 1/7 valuations. No, these are valuations of modulation. Ratio of value equivalent. Okay, so now I'm choosing, actually even for that I could do on the graph, but let me, since I already know the quiver algorithm, because we do everything on quivers. Okay, so modulation, that means that, so I have a quiver, I have Q0, Q1, but then I also have all Fi's, and I also have all the things Bij, Bij's, which satisfy this condition. So that means I have that, right? And then now I need to do valuation, and then valuation will, yeah, I mean modulation. So I have, so we choose Fi. We choose Fi. So these are fields, from Q0, which are fields. And dimension of Fi is root Fi over a common field. Let's say F. Okay. So each of these Fi's, each of these fields has to have dimension Fi over common field.
So they're finite extensions. They're finite extensions of degree Fi.
Yeah. And then the other part is we need bimodules. And Ij and Ji bimodules such that when I write Mi, I mean module over Fi. Right, so this, okay, maybe I'll write once, but this actually means M, FI, FJ. But instead of writing always FI, I'll just do that, okay? And they have to satisfy the conditions with these DIVJs, and I'm just going to write them now. So let me move this. Yeah. I guess when Friday, I'll learn what to do. Okay, so what we need is the. Well, this is what I already wrote, so maybe it's safe to write. Yes. Okay, so. B. No, first I should write this. Okay, so what we need is the com. M-I-J into F-J is isomorphic to the so that is MJ over FJ, right? It has to be isomorphic to the sum of M-I-J into F-I, and all this has to be isomorphic to M-J, J-I, and the dimension, this, so this is dimension of this column over I, work very carefully, dimension of this column, M-I-J, F-J. Now this has extra this I structure here, so the dimension over I is equal to B-J-I. And that is also the dimension of okay, very carefully. Yeah, they just have to match really nicely. Sorry, J over Fj. Yeah, Nij over I. And Nj, so you need, so this is duals, the point, okay, let me say in words, okay. Right, these are binomials. So you have their duals, but you have dual with respect to one thing, dual with respect to the other. These two duals have to match. Okay. And the other bimodule is this common dual of the this, right? Because usually if you have just one module, you can talk about dual with respect to whatever J you have, but here we have a both. So this is dual of Mij with respect to J. This is dual of Mij with respect to I. They have to be isomorphic, and it has to be isomorphic to this other bimodule, which I wrote Mj. And then the numbers have to be this Mij Fj is Fj over Fj. Oh yeah. Oh no. Okay, I'm sorry. Something fine. Yeah. I see it doesn't match because I'm trying to write something else. Well, it's more straightforward what I want to write now. Okay, so that is first thing that you need is bimodule isomorphisms. So that's first thing. And the second thing is about the numbers. that the dimension of Mij over J is equal to Bij. And further, that will be also the dimension of Mji over J, right? And then the dimension of Mij over it has to be Dji, which is the same as the dimension of Mj. So let me,
Override.
do I have some time?
Override, like parentheses, yeah.
Huh?
The parentheses and the extra I that you were writing before,
Here,
yeah.
okay,
Mhm.
okay. Yeah, so now I want to do example.
Mhm.
Okay, so I want to do example, so I want to take this example and modulate, and I want to take this example and modulate. And so. I'm sorry. Okay, so. So I have 1, 1, okay, this is vertex 1, vertex 2, vertex 3, and that one, I have 1, 2. And I have F1 is 1, and F2 is 1, and F3 is 2. Okay. So now I can take, so I need the field like two, so I need the obvious choice is 1 and 2, we take ground reals and complex, but you could take any other field and take extension of the two. So I'm just going to do complex here, real here, and real here.
Mhm.
And then I need the bimodule, so I take C bimodule. Now C on the right side, I do it as a C module, and on the left side, I do it as R. And the other one, Ki is C, and then this is C.
Mhm.
And here between R and R, I can just take R, and R is bimodule itself. Now, there are also fancy things when people do this and they put the different actions, but I'm just doing kind of the very straight. So this now in the other case. I have F1 is 2, and F2 is 2, and F3 is equal to 1. So that means I'm going to put here R, and C here, and C here. Okay. And then the bimodule, okay, again, bimodule here will be C, but now it will be R on the right side and C on the left side, right? And here the both bimodules are C. So usually when it is the same, you just. Because I need, you see, this C. Oh, let me first try with the numbers. I need something. The numbers here, I have 1, 1, and 2, 1. Right, that is what I have. Okay, so let me do modulation underneath. So that means I'm going to put R here, C here, and C here. Now I need the bimodule here, but bimodule which has dimension 1 over this and dimension 1 over this, so that will be C bimodule where I do C as C. And again also C. So usually these, when they don't change, you just kind of treat it the way we did simply like, so the only things that kind of happen different here. So here, again, I have bi module, but now the bi module on the right side is R, and on the right side is. Okay, and so now, let me just write it. Can I?
The other one compared here,
Huh?
the other one compared here.
It's the same
Yeah.
thing.
C, R, C. Okay.
Mhm.
But for the representations, okay, so now I want to talk actually about the representations. So first, I'm going to write here the meaning of representations, and then I'm going to write underneath of the representations by these two. So now, representation of module. So now it has to be quicker, because to talk about representation, I need to know in which direction. Right, so module. So that means I can just choose any orientation here. Okay, so again, it would be B, which will have BI and which will S. I. The only thing is that this is vector space over Fi. Okay.
Mhm.
And then I need for each arrow, I need something. So now I need to go from Vj. And here I have Vi. So again, I'm looking at an arrow from J to I. J to I. But this is Fj vector space. This is Fi vector space. So I don't have max like that. But what I have is I can tensor it with Mij. And now if I over Fj, so if I tensor it with Mij over Fj, then this J structure is used here and I have leftover I structure. Okay, so there is a map here, so this is map B, J, I, which is F, I, and again, the homomorphisms will be J, but now I need to tensor it in J, going to B I, and going to Wj, tensor with Mij, going to Wi, I have Fi here, I have F, okay, so here is identity on Mij, tensor with Fj. So that's the only, and here is this map P Ij, which is for the representation V, and here is P Ij for representation vector. So the only thing is that in the simple based case, all these Mijs are, everything is just the same field. Fi is the same Fj, and Mijs are the same, everything is the same. Okay. And here we can do all right. So let me just do here some representations. Okay, so I'm just choosing this representation. Okay. So obvious symbols are, again, I have to use whatever vector field I have here, and so these are the S1, S2, and S3. Okay. Now just set it in here. Now here I also have a S1, S2, S3. But here S1 has C here, S2 has C here, and S3 has R. Because You see, the represent, let me put the orientation. Because you see, representation means that in each vertex, you have vector space over that corresponding fi. So now I have here my fi's were R, and C. And on the other hand here, fi's are C, and R. So the symbols will be either R, C, depending on what I have. Okay. And then I want to write some other representations. So usually we like to have simple representations and then projectives and so on. So projectives in simple ways. How do you find projectives in simple ways? I just want to remind you. Okay, so in simple ways, projectives. Oh, no, I don't want to write here. Here's my simple ways of this. Let me just add here a little bit more about it. So I just want to write here about projectives. In simple ways, which this board is all simple ways. So you look at your quiver and here's my quiver. Okay. And suppose I want to find projective cover of any of the signals. Okay. So let's say, suppose I want to find, okay, now this cover. I want to find projective, but this, notice the way I pointed them, all my arrows go down. Okay. So if I want to find projective of that symbol, okay, I just follow the paths. So I put K here, follow the path, it will be K here, actually it will be K times this alpha. Then it will be K here, which will be K times this beta. And then it will be K here, which will be K beta gamma. Okay, so you just follow the paths. And that corresponds to the idempotent times so that will be projective of that. So is that okay? So now I want to do this for values. The only thing is I cannot just say K. I take this, I cancel it with whatever bimodule I have, and I'm going to have here tensor, and get back here. And so I'm going to do that, but I just wanted to kind of point out that it is kind of the same idea as it is for simplified, but now just a bit more complicated. Yeah. Okay, so P2, so now I want to do P2 here. So P2, I want to start with 2, so I start with R. Now the bimodule here is R, so I just take that R and tensor it with R, right? So this is my bimodule. You use this depending which way you go. Okay, so what I get here is R tensor R, which is just R. So that means. Okay, so what we just right now, so my P2 is just R and R. And I get it. Okay. And P3, now P3 will be slightly different, right? Because for P3, I have to start with vertex 3 with C. And then I tensor it with my bimodule, which was C and R on the left side. So that means I'm just using left part for the projectives. You will use the second bi-module for the injectors. So I take this, so I have to take C and tensor it with C on the right side, and then I have the left structure. Okay. Now, C tensor with C over C is just C, but because this second coordinate have to be real vector spaces, then I will look at this as being real vector space. So this is actually R. So P3 will have C here, it will have R2 here. Okay, because of this tension with this value. Okay. And then after that, you just have a here by module is R, so you just factor in R and you have the secondary, so you can just put R squared.
So the rule that you're following is that you want all those maps Vij to be the identity map. You want the maps Vij for this module to be the identity.
Yeah,
Exactly. So this is the rule that we're following here. Yeah.
Yeah, that is exactly the same. that I used for
Yes.
there. Yeah, so for
Yeah.
the projective view, thank you.
Yeah.
The projective should take all these maps to be identities, otherwise they don't have to be identities, just simply the case you may have something.
Perfect. Yeah.
Okay. And let me just do here. So now I want to P2. Now this one, oops. So P, oh, sorry. So I want P2, so I have to start at vertex 2. At vertex 2, I have C by module is C, so I take C tensor with C, I'm going to get C. And this map, as you pointed out, this is just data, right? And then for P3, I start with R, but then I take R, and then I have to tensor. Notice my bi-module here is C on the right side R and on the left side C. So when I tensor C R over R, right, this is like identity, so I get just C. But now the vector space here has to be over C, so that's why it will be C. So you see, you tensor over this and you lose R structure, right? And leftover structure is C on the left hand, and that's exactly what you have. So this map here is now this map that should try. So it goes like that. To C. And this is identity map P2, 3.
So the third thing is a C. The third vertex is a C. The left, yeah, that vertex is a C. Yeah. Yeah. Yeah.
I just wanted to take
this.
The same, field, kind of spaces.
You just leave it.
So, I wasn't concerned about that.
Yeah.
So you can see here, we had, just write my P3 now again. I'm just writing P3, I'm not doing anything. P3, so I started with C, then when I tensor it with C, I still have C, but I want to look at this as R vector space, so that's why it's R squared, and then I take identity and it's R squared. Right? So I just rewrote P3 here just to kind of be more clear. Okay? So this is, so now we have all symbols and all.
Yeah, if I may, I2, I want to see I2.
In which one?
Both.
Both. Okay. So I2, okay. You have to start, right? I2, I have to start here, which means I have to start
No, I do want to start from the,
No, my vertex two is in the middle vertex. Which vertex do you want?
no, the model I do, the analogs are the simply laced. Right, I was 0 kk. Over there,
Yeah,
I do, then on the lower one, I do
Yeah.
is over there, 0 kk.
here, this one,
Uh-huh.
okay, so I do, there's several ways of doing injectives, but you can look over the opposite thing.
Ah,
Take
okay, you
injective
started
over
talking
the
about
opposite.
this injective, yeah, I understand.
Okay.
Mm.
Yeah. Actually, there are a few other things that I think I want to add about injective, but definitely you can go over the opposite ring, find projectives, and then, you know.
So, why to in the modulated case, then we'll start in the middle.
Yeah, so. Here, right? So now, if you want I2, you have to start with R here. Okay? And then you have to use this other, like you have to get C here. And we have this, right, so one bi-module. Put the sheet down. You see, I have. I can answer it
Yeah.
now. This
That's
is,
why, see,
okay, yeah, so you can answer it.
yeah, we get C
Yeah,
on the left, 0.
Yeah. It's the definition of injective.
Yeah.
You only go up from
Yeah.
that.
Oh, that's what you said on the left, no, projectives, you follow the path.
Yeah.
Injectives, you follow the path
Yeah.
opposite, which is going against the pillars. Okay, so is that, okay? Okay, so, I guess I should stop now, so I think probably next time I want to do the Auslander writing quizzes. So I will do Auslander writing quiver for something which is simply raised, not that much, but something which is simply raised. And then I will do actually Auslander writing quiver for this and this for me. Perfect.
Thank you. Let's thank Gordana Todorov. Any questions? I have one question. In all examples, the module Mij and Mji were exactly the same modules. And we use that, we work over a commutative ring, which is the field, and we switch the left and right actions.
Yeah,
And over here, when you stated Mij, you did not make an assumption that these were exactly the same modules. You just said that these are bimodules with some properties, or this is a consequence of isomorphism.
this is the dual of Mij.
It's the dual.
Ji is the dual of Mij,
Okay,
and it is dual on both sides.
okay,
So it's
okay.
quite strong, because it has to be dual on one side and dual on the other side. So it's bimodule and then bimodule. I suppose it, so this is bimodule. And this is also bimodule,
Yes.
because you have this I, and right, I is used, but you have extra I structure here, and you have this J structure here, which comes out. So these are really, this is Ji bimodule, and this is Ji bimodule. So the requirement is actually that all of these bimodules are isomorphic.
And in this situation, it turned out to be exactly the same module. That's somehow.
Is when that can be the same. Well, because you see this time, because the dimension
Mhm.
If our dimensions are small, one
I
and
see.
two, then the pi module in one on one side or the other side makes it that field. And so it ends up with the bigger field, but actually, I was doing this with one and two because
Mm.
it's really finite,
Yes.
okay? But we should try something.
Mm. Mm. Mm.
I just thought he was better because yesterday he was really sick. right?
Yeah.
And then today when I saw him, I said, oh, you look better today. Okay, yeah, so if we have,
Mm.
maybe not think of some other examples where, you have
Mm.
field and the bimodule that has to be larger, but then it will get really flat. Right?
Okay.
You see, this,
Mm. Mhm.
this is still staying within finite, right? Because I want to do representation of that
Yes.
and then get the dimension vectors, and then they will match his, tomorrow.
Yes.
That's why I thought that would be good,
Thank you.
but I'll
Yeah,
do also
that's
something.
very kind. Yeah.
Okay.
Mhm. Any other questions?
No
Okay.
more questions.
So let's thank Gordana again for the wonderful help.